Next paper is the in situ NMR spectroscopic studies of copper-based methanol catalysts by Delgada and Angelos.
Well, first of all, I'm not used to talking in a room without a clock, so can I ask the chairman to stop me when my time has run out? The work I want to talk about today has been done in our laboratory by Abdallah bin Dada, postdoc, and John Cobb, PhD student. And I think there are three things that I must first talk about from the title. First of all, what do we mean by in situ? What do we think that NMR can do for us? And finally, why did we choose to look at methanol synthesis? In a perfect world, what in situ should mean is essentially that we have our catalytic reactor inside our spectroscopic cell, and we take measurements on the working catalyst in the catalytic reactor. We're trying to get there, but we're not there yet. So for this talk I have a slightly different definition of in situ, one that I think is not often admitted to, but in situ are the conditions inside my cell. That is too easy though, so there are two further conditions that we insist upon. The first is that the catalyst is activated inside the spectroscopic cell. That is so we can be sure that there is no degradation of the catalyst sample between activation and carrying out the spectroscopic measurement. The other thing that we insist upon is that the cell is not sealed. This is so we can carry out sequential experiments. We can dose one probe molecule, pump out, dose another, or put in a second amount of the first. Of course, what sort of conditions can be achieved in our spectroscopic cell? And if we look just down the right-hand side, we can get a wide range of pressures from, in fact, the lowest we can measure is 10 to the minus 3, 1 millibar. That's the detection limit of our pressure sensor. And we can go up to 200 bar. The temperature range from 213 to 500 Kelvin. All the experiments that I will show you have been carried out in a batch mode, although we have already carried out a few experiments on a flowing system. Mixing in a gas flow is obvious. And what is the detection limit of the NMR experiment? Well, I hope to show you today that the detection limit can be less than 1 monolaire on these high surface area catalysts. The NMR probe itself is shown here. You don't have a pointer. We have a catalyst bed contained in a Pyrex Can we see that? Catalyst bed contained in a Pyrex reactor, about 5 centimeters long and about 8 millimeters internal diameter. Outside of the Pyrex microreactor, we place our NMR coils, this line down here. The catalyst bed is then suspended from a pressure plug, through which we can pass gas down into the catalyst bed, and we have some electronic feed-throughs to take the NMR signal out. And of course we have some thermocouples to measure the temperature in the catalyst bed and to measure the temperature of the pressure vessel. This system is then placed inside a metal pressure vessel, and a seal is made at this point using a copper-lead sandwich. Of course, once we are inside the pressure vessel, we then have heating and cooling apparatus that goes around outside, and finally the whole assembly is placed inside the NMR magnet. We can admit, as I've said, gases through the top, we can exhaust them through the bottom, or we can operate in reverse mode if that is easier for the experiment. That very quickly is how we do the experiment. What can NMR tell us? There are several things that NMR can do, but there are only, I think, 3 things that I want to talk about today. We can attempt some structural characterization via the chemical shift. This arises from the magnetic fields that are set up by the bonding electrons. The electrons in chemical bonds will give us the chemical shift. Also, we get a thing called the night shift. This arises from interaction of the nucleus with metal conduction electrons. So we now have a very easy way of differentiating between a species that's adsorbed on a metal that will show a night shift that will be very large, or a species that's adsorbed on an insulator where we will only see the chemical shift, which will be quite small. The other thing that we will see is that NMR can tell us about the mobilities of the adsorbed species. If we consider a rigid molecule, then there are some very large line broadening interactions. These can be dipolar interactions or the chemical shift anisotropy. Both these effects have an angular dependence, 3 cos squared theta minus 1. So if the species is rigid, that angular dependence is not averaged out, and we get very wide lines. If we go to the extreme of a liquid sample, the species are then very mobile, and the 3 cos squared theta minus 1 term averages to 0, and we get a very narrow line. We will be looking at surface adsorbates that are somewhere in between. So the averaging will be greater or lesser, and we will see a wider or narrower line the other way around. So that's the by way of introduction. We chose to look at methanol synthesis catalysts because we had a new technique. We had no database that we could use to assign our spectra, so we wanted to look at a system that was already fairly well understood. This would help with the interpretation. The first thing that we chose to look at was the adsorption of hydrogen gas on supported copper catalysts. Hydrogen adsorbing on a metal, of course, is a very good thing to look at by NMR because the hydrogen tends to be very mobile. And this will average out the line broadening interactions, so we should get quite narrow lines. What I show here is the adsorption of hydrogen on copper zinc oxide. Get this right. If we look at this first spectrum, we can see there's quite an intense resonance, about 85 ppm. That's a large shift, a night shift. That tells us that the hydrogen is adsorbing on metallic copper sites. This large scroll here is an instrumental artifact. It means nothing. What we then did was we evacuated the system, I say down to 0.1 millibar, because we cannot measure below 0.1 millibar. I suspect we are perhaps 2 orders of magnitude vacuum below this. at room temperature. And we see rapid desorption of the hydrogen on copper. I think that's what we would expect. Something that we did not expect was that even after 1 hour's evacuation, we could not remove all the hydrogen on copper. And in fact, depending on the exact history of the sample, we can pump for many hours and still see hydrogen on copper. What we think this might be is hydrogen that is somehow trapped on the copper or in the copper. This has been suggested by, for example, Ken Wall at ICI. He talks about hydrogen trapped beneath a layer of copper oxide on the surface. So maybe this is this trapped hydrogen. The other thing that we can notice is that as the surface coverage of hydrogen decreases, we see a further downfield shift in the position of the resonance. And we think this is simply a surface coverage effect, getting a slightly greater night shift as the surface coverage of hydrogen goes down. But when we go back to the sticky hydrogen, where we've removed the surface hydrogen, the position of the resonance moves back towards zero. I think, again, showing that perhaps this is somehow slightly different hydrogen on copper from the species that we're seeing here. I mentioned the pressure effect already. Here now we're going the other way. We're starting from 11 millibar of hydrogen and increasing the pressure up to almost 2 atmospheres. And we can see now, of course, because we're increasing pressure with surface coverage, the night shift is getting less. As I said, that might just be a surface coverage effect. Another possibility, because the line is getting wider, is that we may be seeing exchange. That the hydrogen on the copper is starting to exchange with hydrogen on a non-metallic site. That may be the zinc oxide, or it may indeed be with the gas. At this stage we have no way of differentiating those two possibilities. If we carry out these experiments on zinc oxide, copper zinc oxide alumina, or copper silica, we see much the same type of NMR spectrum. If, on the other hand, we look at copper alumina, we see something slightly different. Here now I've shown the full spectrum, so we can see the resonance due to gaseous hydrogen. We're at half an atmosphere. But now we can see quite clearly two well-resolved resonances in the night-shifted region. This is telling us that there must be two adsorption sites on metallic copper or hydrogen on the copper alumina catalyst. The other thing that we can say, because NMR is quite a slow technique, is that there must be only very slow exchange between those two copper sites, because we can resolve them. Now, what might those two copper sites be? One possibility may be that we have crystallites of different sizes, and we're seeing adsorption on bigger and smaller copper crystallites. However, these catalysts were all prepared for us by ICI, and they think that that is not the explanation. They think that the copper crystallite size and particle size dispersion on copper alumina is the same as their copper zinc oxide alumina. So the particle size, unless we're seeing sintering, doesn't seem to be the explanation. Another possibility might be that we're seeing adsorption on different copper faces. How might that work? I'm not claiming that these are the faces, but on the close-packed surface, for example, 111, the hydrogen has to sit up on the top of the surface. Whereas on a more open surface, there is the possibility that the hydrogen can get down further into the metal. And now you can argue several ways. You can say 111 has a higher surface electron density and therefore will give you a bigger night shift. Or you can say that the more open surface allows the hydrogen to get further in. Again, that might give you a bigger night shift. So we can't say which face or which effect is dominating. All we can say is there must be two adsorption sites. We repeated the experiment, but this time we activated in 100% CO, copper alumina. And this time we only see the broad adsorption, single adsorption site. Now, this is a very recent experiment. We haven't yet done any more, so we don't know at this stage if we have left CO selectively on one adsorption site, blocking it out to hydrogen, or has the adsorption produced a different surface, has the activation with CO produced a different surface. So to summarize, on clean surfaces, hydrogen adsorbs on metallic copper. On partially oxidized surfaces, sticky hydrogen can be seen. And this may be hydrogen locked in by surface oxygen. The oxide support affects the adsorption of hydrogen on copper and can self-adsorb hydrogen. We know that from other experiments, other people's work. And on copper alumina, we can clearly resolve two metallic adsorption sites. How much time am I? Time? 2 minutes. So, we've also looked at the adsorption and temperature programmed reaction of formic acid on these catalysts. We can now take spectra every 25-30 seconds. We admit formic acid to the reactor, we see these two peaks that vanish. That's telling us that we must adsorb the formic acid onto the catalyst to give us a very immobile species. And we think this might be bidentate formate. We've done this on many, many different catalysts. If we carry out a similar reaction on copper zinc oxide alumina now, we get generation of the night shifted peak, confirming that the adsorption is dissociative and protons are ending up on the copper metal separated from the formate. And just to convince you that we do have things present when we see nothing, this is the temperature programmed reaction spectra of formic acid on copper zinc oxide alumina. Here we've adsorbed formic acid, only immobile species are present, and the metallic hydrogen, copper, hydrogen on metallic copper. As soon as we warm up, we lose the hydrogen from the metallic side, and we start to see broad bands appearing in the chemically shifted region. These must be due to formate. I don't think there's any other possibility. One feature that we do see here downfield is this shoulder which arises. We're not sure what this may be, but we think this might be copper formate, with the formate hydrogen not being completely isolated from the metallic conduction band. If we cool down again, we get readsorption of hydrogen onto the metallic copper sites, showing us that the decomposition of formate on copper finishes up still with a metallic copper surface. If we do a quick evacuation, we lose all of this resonance, telling us that this resonance must be hydrogen gas. So we've decomposed the formate to carbonates and hydrogen gas. So I think I've had my time there. That's the summary. Finally, I must thank you for putting up with me, and the people that funded this work, the SERC and ICR.
Any questions or comments? Yes.
Is there any possibility to consider that you might have molecular hydrogen along with dissociated hydrogen as giving a separate night shift behavior?
It is possible to devise an experiment that would tell us that. If we absorbed HD onto the surface, we could then do an experiment, for example, where we irradiated the deuterium and looked to see if there was any effect on the resonance of hydrogen. If we had molecularly absorbed HD, we would see a perturbation of the hydrogen resonance when we irradiate deuterium. If we had atomic H and atomic D, then there should be no effect. So in theory it's possible to do that experiment. We looked at the price of HD and decided that financial constraints made it impossible.
Can you exclude the possibility that hydrogen spill over from the copper to zinc oxide and distinguish between these two species?
There is. We think that where was it? We can see here that we do get a shift upfield. Now that shift may be due to the type of effect that you are talking about. And one way that we could do that is if we could try and irradiate, say, exactly the copper site in the absence of spillover and look to see if that has any effect on the resonance here. If there is exchange, then the true resonance position of hydrogen on metallic copper will be perhaps somewhere down here. And if we irradiate here, even although we see no NMR resonance, if there is exchange between a site, say here and somewhere over here, then it will have some effect on the exchanging hydrogen and on the resonance of the exchanging hydrogen. So it is possible, but we haven't done it.
Thank you very much.